Hi, everyone. Today is March 22nd. So I'm going to put the date on here. And today what we're going to talk about is the Taylor series. And what we're going to use is we're going to create a polynomial that fits all of these conditions. Okay, so we're going to construct a polynomial. P of x is equal to a sub 0 plus a sub 1 times x to the first power. We wouldn't really write the 1 there normally, plus a sub 2 x squared plus a sub 3 x cubed plus a sub 4 x to the fourth. Okay, all these a sub 0s, a sub 1s, a sub 2s, a sub 3, a sub 4s, those are all they're gonna be coefficients for this polynomial that we're gonna construct. Okay, so we already know p of x is this. Okay, so what would the derivative of p of x be? And that'd be p prime. So I'm gonna write p prime of x. Okay, now a sub 0, let's write equals here. A sub 0 right here is a constant. So when I take the derivative of it, it's going to be 0. Okay, so I'm not going to write it because it'll just be 0. This first one is going to be, okay, we're going to bring this power down and it'd be 1 times a sub 1 x to the 0. And then we're not going to write that because that's going to be 1. Okay, and then plus 2 times a sub 2 times x, because that power is going to drop by 1 and we brought the power down. We're just using the power rule here. Okay, and then the next one would be plus, bring the power down, so it's going to be 3 times a sub 3 x to the second power, and then plus, and then 4 times a sub 4 x to the third power. Okay, and that'd be the first derivative. Okay, and then we got to take the second derivative because I went all the way down to the fourth derivative. Okay, and so p double prime of x, okay, would be, this is 1 times a sub 1. Well, a sub 1 is a constant, so 1 times that would also be a constant. So when I take the derivative of this, it would be 0. Okay, and then I'm going to write this a different way. You're not going to know quite right now why I'm writing it that way, but I'm going to bring this power down. There's going to be a pattern that shows up, okay? So I'm going to bring this power that's 1 right here. Actually, I'm going to go ahead and write 1 right here. I'm going to bring that power down, and this one's going to be 2 times 1, and I'm actually going to put parentheses around that. You wouldn't have to, okay? And then times a sub 2, and then this one would become x to the 0, and we're not going to bother with that one because it'd just be 1, okay? And then plus, and then this one's going to be 3 times 2, and I'm going to put parentheses around that, times a sub 3 x, because the power is going to drop by 1 there. All right, and then this next one's going to be plus 4 times, the power is going to drop down, so that'd be 3 times, and I'm going to put parentheses around that, 4 times 3 times a sub 4 x squared. Okay, so now we got to go to the third derivative. Okay, the third derivative of x. Okay, this is going to drop out, and this is going to become 0, okay, when I take the derivative of it. This one's going to be, we're going to bring the power down, and this one's going to be 3 times 2 times 1, close the parenthesis, times a sub 3, and this time we're not going to write x because it'd be x to the 0, and then plus, and then this one would be, notice the terms are dropping down by 1 each time, and this would be 4 times 3 times 2 times a sub 4 x cubed. No, I'm sorry, x to the first, right? Let me get my white out. X to the first, because we're reducing 1, right? We brought the power down. We brought the power down, and that's going to go from 2 to a 1. Okay? All right, so then the fourth derivative of this polynomial of x would equal, okay, so now this one's going to be the one that's 0, and then this one's going to be 4 times 3 times 2 times 1, close the parenthesis, times a sub 4, okay? And so we're going to see something when we start figuring these out. Okay, what are the values of a sub 4 and a sub 1 and a sub 2 and a sub 3, all those a subs, okay? All right. Okay, so now what we're going to do next is we look at p of 0 is equal to 5. So this is p of 0. Okay, if I put 0 in here for x, right, we're going to calculate p, okay, of 0. Okay, so it'd be 1 times a sub 1 plus 2 times a sub 2, 0, because x is 0 now to the first. So that's going to make this become 0 because our x is 0. Plus 3 times a sub 3, 0 squared. This one's going to be 0. Plus 4 times a sub 4, 0 cubed. This one's going to be 0. So we really have 1 times a sub 1. I take that back. We have 1 times a sub 0. Let's make that a 0, okay? 1 times a sub 0, because we're using this one, not this one, okay? All right, now there isn't a 1 in the original problem. There wasn't a 1 here. I'm putting a 1 there. You're going to see in a minute why, okay? Let me talk about this in just a minute. There's going to be factorials involved in this, okay? So this becomes p of 0, which is equal to, okay, so I don't know if we remember this from factorials, but 1 can be written as 0 factorial times a sub 0, okay? So 0 factorial is defined as being 1, okay? So now what is a sub 0? Okay, and there's going to be a pattern that you're going to see in this. So p of 0, and to find a sub 0, I'm just going to divide both sides by 0 factorial in this case. So p sub 0 divided by 0 factorial will give me a sub 0. And I know p of 0 from my list up here, that p of 0 is 5. So this is 5 over 0 factorial, which is a sub 0. Now this is the most important part right here. That's where you're going to see your pattern. So this is 5 divided by 1, and 5 divided by 1 is 5. So I know 5 is equal to a sub 0. Okay, well, how about p prime of 0? Okay, so I know p prime of 0 is equal to, okay, so we're going to use this one this time. Okay, so we're going to have this still, but because we're putting 0 in for x, this one's going to be 0, this one's going to be 0, and then this one's going to be 0. Okay, so that would be 1 times a sub 1. All right, dividing this 1 right here is really 1 factorial. So p prime of 0 is equal to 1 factorial. 1 factorial is also 1 times a sub 1. So 0 factorial and 1 factorial are both 1. Okay, and so then we have p prime of 0 divided by 1 factorial is equal to a sub 1. Well, we know from up here, p prime of 0 is 7. So this is going to be 7 over 1 factorial. That'd be a sub 1. Well, that'd be 7 over 1, which is 7. So 7 is equal to a sub 1. So we now know a sub 1. Okay, so how about a sub 2? Okay, so we go to the second derivative. P double prime of 0 is equal to 11. So I'm going to use this one. I'm going to plug in 0 into P double prime. That would cause this one to be 0 because there's an x right here, and would cause this one to be 0 because there's an x right there. So this P double prime of 0 is equal to, and this is why I wrote the in parentheses, 2 times 1 times a sub 2. So that'd be P double prime of 0 is equal to 2 times 1. Well, that's 2 factorial times a sub 2. So P double prime of 0 over 2 factorial would equal a sub 2. All right, so P double prime 0, P double prime 0 is 11. So this would be 11 over 2 factorial. And 2 factorial is 2 times 1, so that's 2. So this would be 11 halves. 11 halves is our a sub 2. Okay, p triple prime. Okay, p triple prime of 0 is equal to, okay, so here's p triple prime. It's 3 times 2 times 1 times a sub 3. Well, here's where our x is, right? But when we put 0 in here for x, this x is going to be 0. So all of this is going to go away, and I'm going to be left with 3 times 2 times, you're starting to see the pattern. So this is 3 times 2 times 1 times a sub 3. That becomes p triple prime of 0 is equal to 3 factorial, triple prime, 3 factorial, seen it? A sub 3. So then this is p triple prime of 0 divided by 3 factorial is equal to a sub 3. P triple prime of 0 is 13. So this would be 13 over 3 factorial is equal to a sub 3. Okay. Now, what's 3 factorial? Well, that's 3 times 2, right, times 1. So that'd be 6. So this would be 13 over 6 would equal your a sub 3. Okay, the last one we have is a sub 4. Okay, so we're going to take, we know that the fourth derivative, I can slide this up for you to see it. Okay, the fourth derivative at 0 is equal to, I'm going to slide it down so we can look at that fourth derivative. Okay, your fourth derivative is 4 times 3 times 2 times 1 times a sub 4, right? So this would be 4 times 3 times 2 times 1 times a sub 4. Well, that's just 4 factorial. So the fourth derivative at 0 is equal to 4 factorial times a sub 4. The fourth derivative at 0 divided by 4 factorial would equal a sub 4. And the fourth derivative at 0 is, if you look up here, 17. So this is 17 over 4 factorial. That would be your a sub 4. That'd be your actually it's your fifth term, right? Because 1, 2, you guys can't see it. 1, 2, 3, 4, 5. It'd be the coefficient for the fourth power term, right? Okay, and then 4 factorial is 4 times 3, 12, times 2, 24, times 1, 24. So this is 17 over 24, and that would be a sub 4. Let me slide it up. 17 over 24 is equal to your a sub 4. Okay, so we just created a polynomial that where if you put 0 into the fourth derivative, we get 17. If you put 0 into the third derivative, you get 13. All of these would work, okay? And the polynomial that would, where all of these conditions would work is this. So our polynomial becomes this: p of x is equal to our constant, which is a sub 0. Let me slide up so you can see. Yeah, you really can't see it and see my writing at the same time. So I'm just putting them all in this, okay? All right. So it's going to be p of x would be 5 plus 7x plus 11 halves x squared plus 13/6 x cubed plus 17/24 x to the fourth. And if we took the derivative, the first derivative, the second derivative, the third derivative, and the fourth derivative, and we put 0 into this polynomial for those derivatives, we would get all of these values out. Okay? Turn the page and we'll go to the next one. I know I said to turn to the next page, but I actually want to do something a little bit different. Okay, I forgot to say something to you guys. So turn it back to the first page. Okay, and I kind of mentioned at this, but I really want to be specific with you guys. Okay, especially how do you? Okay, so we came up with a polynomial that matches all this criteria, right? Okay, this is going to help us for the next example. Okay, So how do we get the a sub 1? The term, the coefficient for the x to the first term, okay? Well, it was the first derivative over 1 factorial at 0, right? And how do we get the term, the coefficient, okay, for the x squared term? Well, we had to find the second derivative over 2 factorial. So there's a pattern here, right? How do we get the coefficient for the x cubed term? Okay, we had to take the third derivative over 3 factorial. And then the coefficient for the fourth term, well, we had to take the fourth derivative at 0 divided by 4 factorial. Okay, so fourth derivative over 4 factorial at this value, right? And that gave us the coefficient for x to the fourth. And this one gave us the coefficient for x cubed. And this one gave us the coefficient for x squared, and so on, okay? So this one is, you can think of this as being the function, the polynomial itself, the 0th derivative over 0 factorial. That's why I wrote 0 factorial and just didn't leave it as 1, okay? So there's definitely a pattern. So this is the first derivative over 1 factorial, second derivative over 2 factorial, third derivative over 3 factorial. The 0th, you can think of this as being the 0th derivative over 0 factorial. So we could even go further with this. If we knew the fifth derivative at 0, we would find the fifth derivative of the polynomial at 0, and we would divide it by 5 factorial, and that would give us the coefficient for the x to the fifth term. That would be the next one if we wanted to go further, okay? All right, so now let's turn the page and go to example 1, okay? Thanks. So the next example is, we're building on this to kind of understand this a little bit better. So where we're going with this is, we can create a polynomial function that mimics our function. And that's what the whole thing about Taylor polynomials and Taylor series and all that's all about. Okay, so right, so we want to construct a polynomial. P of x is equal to a sub 0 plus a sub 1 x to the first plus a sub 2 x squared plus a sub 3 x cubed plus a sub 4. It's the same size polynomial as before, the fourth degree polynomial, that matches the behavior of natural log of 1 plus x at x equals 0 through its first 4 derivatives. Okay, so we're gonna go 4 derivatives, and we're gonna need to go 4 derivatives because, why 4 derivatives? Because we need to know the fourth derivative, because that we're gonna use that to get this a sub 4. Okay. All right, so we know f of x. We're just going to go through first, and we're going to do all these derivatives, okay? We're going to do the first 4 derivatives for ln of 1 plus x. So let's start out with calling this f of x. So f of x is equal to ln of 1 plus x. Okay, so now we're going to go through, okay, what's the first derivative of that? Well, the derivative of natural log is 1 over what this is times the derivative, the chain rule, right, times the derivative of this. Yeah. Okay, so this would be 1 over 1 plus x times the derivative of 1 plus x, which would just be 1. Now, I'm going to rewrite this. We probably use this one if this is where we're going to stop, but this one's going to be hard to find the derivative of. So what I want to do instead is I want to rewrite this, and I'm going to choose to rewrite this as 1 plus x raised to the negative 1 power, and that's the same as this. It's just this is going to be a little bit easier to do multiple derivatives with, okay? All right, so the next one is f double prime of x. Okay, so we're going to take the derivative. We're going to use this to find the derivative. So it's going to be negative 1, so power down, 1 plus x raised to the, and I need to subtract 1 from this, so it's going to become negative 2 times the derivative of this, of 1 plus x, which would just be 1. Okay, now this is going to wind up being negative 1 over 1 plus x squared. Okay, now harder to do the derivative with this one, easier to do it with this one. Okay, so the third derivative, we're going to use this one. So the third derivative at x is equal to, okay, and power down, so that'd be negative 1 times negative 2, which would be 2 times 1 plus x raised to the negative 3 power. Okay, so that becomes 2 over 1 plus x cubed. Again, it's going to be easier to take the fourth derivative from this one than this one. Okay, so the fourth derivative at x would be -6, because 2 times -3 is -6, times 1 plus x raised to the -4 power. Better way of writing that is -6 over 1 plus x to the 4th power. You know what? I didn't say this, okay, but we took the derivative of 1 plus x, which is 1, and we should be multiplying that right here, and it's just 1, right? So that's why I didn't write it. So 1 plus x to the 4th power. Okay, now, before we were given the derivatives, you know, p of 0 is this, and p prime of 0, okay? This is a little bit different. We're trying to match this function, not the polynomial. So we want to create a polynomial that's the same as this one, right? So we're going to find what is f of 0. Okay, so f of 0 would be the natural log of 1 plus 0, right? 1 plus 0, which would be 1. And that would be 0, right? Okay. All right. Now what's f? And this is like our p of 0 in the last problem, okay? It's just we have the function now, okay? So what is f prime at 0? And you know what? I didn't say this. Why am I doing it at 0? It's because it's at x equals 0 right here. That's why I'm doing this, okay? So I want to put it into this one, right? Okay, so this would be 1 over 1 plus 0. So that becomes 1 over 1, which is 1. And then the second, that's why I rewrote them over here. It's going to be a little bit easier to calculate with these, though, instead of these. These were easier to find the derivative, easier to put numbers into these, though, okay? So for this one, f double prime of 0 would be -1, and this would be 1 plus 0, right? So 1 plus 0 is 1, and squared is 1, so this would just turn out to be -1. So the second derivative of 0 is -1, okay? And then f triple prime at 0 would be 2 over 1 plus this one right here, right? 1 plus 0, which is 1, and cubed, right? Which would be 1. So this becomes 2. And then this one, the fourth derivative at 0 is -6 over 1 plus 0, which is 1 to the 4th. So that'd be 1. So this becomes -6. So this is we're using the function to find the derivatives, because these are the derivatives that I want for this polynomial, okay? All right, so now how do I find this a sub 0? Quick and easy way. We don't have to go through all the work that we did before, okay? All we have to do is look at that pattern that I showed you, okay? And that was the whole point of that first problem, okay? Is a sub 0, and this is what I really want you to understand, would be the function, right? The 0th derivative, which would actually be the function at 0 over 0 factorial. Now that's really going to be 1, right? Because 0 factorial is 1. So f of 0 was 0 over 0 factorial, which is 1. So this comes out to be 0, okay? All right, I'm going to slide this up a little bit. Okay, now what's a sub 1? Well, to find a sub 1, I have to use the first derivative, so f prime at 0 over 1 factorial. Well, what was f prime of 0? F prime of 0 was 1. Now you have to maybe look above. Okay, I'm not going to slide the paper down. So 1 over 1 factorial, right? 1 factorial is 1. So that'd be 1 over 1, which is 1. Okay. This is my constant that I'm going to have for my polynomial. This is going to be the coefficient for x to the first power. So all these numbers kind of match up, okay? And then a sub 2 would equal f double prime of 0 over 2 factorial, right? And from up above, we saw f double prime of 0 was -1. So that's be -1 over 2 factorial, which is 2 times 1, which is 2. Okay, so a sub 2 is -1/2. Now that's going to be the coefficient for our x squared term, okay? And then a sub 3 is going to be f triple prime at 0 divided by 3 factorial. Okay, so f triple prime of 0 was 2. So this is 2 over 3 factorial. 3 factorial is 3 times 2 times 1. So 3 times 2 is 6, times 1 is still 6. So this is 2 6, but we'll really reduce that and make it 1/3. Now, this is going to be the coefficient for our x cubed term, all right? And then a sub 4. That'd be the fourth derivative at 0 divided by 4 factorial. Okay, the fourth derivative at 0 was -6. That's right here, right? Okay, so -6 over 4 factorial. Well, 4 factorial is 4 times 3, which is 12, times 2, which is 24, times 1, which is still 24. So it's -6 over 24. Better way of writing that is -1/4. Okay, so what's our polynomial function that will mimic the natural log of 1 plus x for the first 4 derivatives? Okay, so what that would look like is p of x is going to equal. Now, normally for polynomials, we write them from the highest power to the lowest power. Okay, so this would be the fourth power. We normally write it first. I know I didn't write it that way at the top, okay, but that's normally how we write it, okay? So this becomes, remember, this is our x to the fourth, so that's our highest power. So it's going to be -1/4 x to the fourth. And then this is our coefficient for x cubed, so it's going to be a positive. So plus 1/3 x cubed. And this is the coefficient for our x squared term, and it's negative, right? So I'm going to write minus 1/2 x squared. And this is our coefficient for x, so it'll just be plus 1x, so just plus x. And then our last term, which is our constant term, is a sub 0, and it's 0, so we're not going to write it because it's just 0. Okay, so this polynomial that we wrote, -1/4 x to the fourth plus 1/3 x cubed minus 1/2 x squared plus x mimics, okay, the natural log of 1 plus x for the first 4 derivatives, okay? And that's what I'm trying to show you here. This is going to be turning into what's called the Taylor polynomial, all right? Okay, so the next example, all right? Example 2. Use the method from the previous examples to find the fourth degree polynomial that approximates the behavior of f of x equal to the square root of 1 plus 2x at x equals 0. Okay, so if we want to do a fourth degree polynomial, okay, we're going to need to know the first derivative, the second derivative, the third derivative, and the fourth derivative of f of x at x equals 0. So I'm going to need all of that information to get this polynomial, okay? And then it's going to be very similar to what we've been doing, okay? All right, so right off, the 0th derivative, which is the function, right, is f of x is equal to the square root of 1 plus 2x. And a better way of writing that to find the derivatives would be in parentheses 1 plus 2x raised to the 1/2 power. Okay, so what's f prime of x? And I like to always do the derivatives first and then start putting them in. You could do it this way. You could find the function, put 0 in. Find the first derivative, put 0 in. Second derivative, put 0 in, okay? You could do it that way. There's no problem with that, okay? Because at the end of the day, nobody's going to know which one you did first, right? If you did all the derivatives or if you found the values first, okay? I just like to do all the derivatives first, okay? So f prime of x is equal to, okay, so power down, so it'd be 1/2 times 1 plus 2x, okay, and then I got to subtract 1 from this, so that's going to make it -1/2. Okay, so now we can't forget this. Okay, we brought the power down, we subtract 1 from the power, we got to use the chain rule. What's the derivative of 1 plus 2x? Well, it's 2, right? Okay, so now we have 1/2 times 2. Well, that'll be 1. So this becomes just simply 1 plus 2x raised to the -1/2. Okay, so that's really 1 over 1 plus 2x raised to the 1/2 power. Okay, I'm a little crooked there, sorry. All right, so now the second derivative of x. Okay, hang in there, buckaroos. All right, hang in there, hang in there. Okay. Okay, so the second derivative, okay, I would use this one to find the second derivative. So that's going to be negative 1/2 times 1 plus 2x. I'm going to subtract 1, so that's really subtracting 2 halves from this, which makes negative 3 halves. And then times the derivative of 1 plus 2x, which would be 2 again, right? And now I have negative 1/2 times 2. Well, that's negative 1, right? So that's negative 1 times 1 plus 2x raised to the negative 3 halves power, right? For putting values in, it'd be easier if we, I wrote that wrong. Negative 3 halves, right? Okay. So then this becomes a negative 1 over 1 plus 2x raised to the 3 halves power. Okay, 2 more derivatives, right? So we need to do the third derivative. Okay, why do we need to do all the way to the fourth derivative? Because we want to find the fourth degree polynomial, and we need that fourth derivative to use that to find the coefficient of x to the fourth. Okay, so the third derivative at x would be, I'm going to use this one. Okay, so it's going to be negative 1 times negative 3 halves. So that'd be 3 halves times 1 plus 2x. And I'm going to subtract 1 from this, so that'd be subtracting 2 halves, so that would give me negative 5 halves times the derivative of the inside, which would be 2 again, right? So your 2's cancel here, you're going to be left with a coefficient of 3 on this. So it'd be 3 times 1 plus 2x to the negative 5 halves power. That would be 3 over 1 plus 2x to the 5 halves power. Okay. This one's going to be better to find the derivative for, okay? So the fourth derivative of x would be equal to 3 times negative 5 halves, so that'd be negative 15 halves times 1 plus 2x. And we got to subtract 1 from this, so that makes negative 7 halves times derivative of the inside, right, which is 2 again. And so here my 2's cancel again, and I'd be left with negative 15 times 1 plus 2x raised to the negative 7 halves, or negative 15 over 1 plus 2x to the 7 halves, okay? So now let's go back up. Let's find f of 0, f prime of 0, f double prime of 0, f triple prime of 0, and the fourth derivative of f at 0, okay? So f of 0, okay? So that'd be 1 plus 2 times 0, right? So that'd be 2 times 0 is 0. So this just be 1 to the 1/2, or the square root of 1, which is 1. All right. The next one, f prime of 0, that'd be putting 0 in right here for this x. That would cause this to be 0. This would cause the parentheses inside the parentheses to become 1. 1 to the 1/2 is 1. 1 divided by 1 is 1. So it's 1 again, right? All right. And then the second derivative at 0, that'd be this one. So it's going to be negative 1 over, this would again be 1, right? 1 to the 3 halves, and that'd still be 1. So this is negative 1. And then right here, the third derivative at 0 would be this inside the parentheses would be 1 again, right? So it'd just be 3. And the fourth derivative, whoops. Let me get my whiteout. I'm still using whiteout. Okay. Okay, the fourth derivative at 0 would be negative 15 over 1, which would give you just negative 15. Okay, so a sub 0, right? To find that coefficient of that first term, okay? of the 0th derivative, which is that function, right? So this was equivalent to f of 0 over 0 factorial, right? And f of 0 was 1 over 0 factorial, which is 1. So this is 1 over 1, which is 1. Okay, so now I'm going to do a sub 1. All right, a sub 1, that's equal to f prime of 1 over 1 factorial. Hopefully this is coming, like I'm doing this so much that it's like, okay, I finally get it. Okay, f prime of 1, or not f prime of 1, f prime of 0. F prime of 0 over 1 factorial. F prime of 0 from above was 1 over 1 factorial, which is 1. So that's also 1. And that's going to be my coefficient for my x term. All right. A sub 2 is the second derivative at 0 over 2 factorial. The second derivative at 0 was negative 1. So that's going to be negative 1 over 2 factorial, which is 2. And then the third, a sub 3, would be f triple prime at 0 over 3 factorial. F triple prime of 0 would be 3 over 3 factorial, which would be 3 times 2, which is times 1, which would be 6. So this is 1/2. And then finally our fourth one for the fourth degree coefficient, or x to the fourth term. Okay, a sub 4 would be f of the fourth derivative at 0 over 4 factorial. All right, and that would give us negative 15 over 4 factorial, which is 24. And that can be reduced. Both are divisible by 3, right? So that becomes negative 5 over 8. Okay, so use a method from the previous example to find a fourth degree polynomial, okay? So because we found a sub 4, that's the coefficient for x to the fourth, so that would be the fourth degree, right? So p of x would equal a sub 0, which is 1, or I told you right from highest power to lowest power, right? If you wrote it the other way, you would not be wrong, okay? It's just normally written from the highest power to the lowest power. This is the highest power right here, right? The a sub 4. So that'd be negative 5/8 x to the fourth, and then plus, because it's positive 1/2 x cubed, and then a sub 2 is negative 1/2, so I'm going to write minus 1/2 x squared, and then a sub 1 is 1, so that just be plus 1x, or just x, and then plus 1. Okay, and so this polynomial right here, okay, this polynomial, let me slide this up a little bit. This polynomial right here mimics our function, okay, for four derivatives. It's the same thing, okay? It mimics it. All right. Okay, guys, for the next one, I want to go to the definition. Okay, so we've been building up on this, on the examples we've been doing, and the first problem that we did to build up to this. Okay, so the definition of a Taylor series generated by f at x equals 0. When a Taylor series is generated at x equals 0, there's a more of a specific name. It's called a Maclaurin series. Okay, so Taylor series don't always have to be centered at x equals 0. When they're centered at x equals 0, a Taylor series is called a Maclaurin series. Okay, just technical information for you guys. All right, so let f be a function with derivatives of all orders throughout some open interval. Okay, then the Taylor series generated by f. We've been doing this, right? Okay, so we've been doing this Taylor series. If we go forever with it, okay, which is impossible to do, but if we were able to do it, okay, we would get this, and it would be k equals 0 to infinity. All right, and then the partial sums, okay, that's what we've been doing. We've been stopping it like at the fourth derivative, okay? And that would be a Taylor polynomial of order 4, because we've been stopping it at the 4th degree, okay? So again, when it's centered at x equals 0, Taylor series is called a Maclaurin series. I think on the AP exam, you won't see them call it a Maclaurin. They'll just call them all Taylor series. So if it was x equals 3, okay, that would definitely be a Taylor series, okay? And what would be different about it is we start shifting all this over. So it'd just be x minus 3, x minus 3, everywhere you see x. It's just a translation to the right 3 is all it is, okay? All right, so for this next problem, okay, we want to construct the 7th order Taylor polynomial and then the Taylor series for sine x at x equals 0. So the 7th order, that means I need to go all the way up to the 7th derivative for sine of x, and I need to find all those derivatives at x equals 0, okay? So let's just jump in and start, okay? So f of x is equal to sine of x, and then f prime of x, the derivative of sine x is cosine of x. I'm going to slide this up so you guys can see it. Make sure you guys see it. All right. And then f double prime of x. So the derivative of cosine of x is negative sine x. And the third derivative at x would be the derivative of negative sine x, okay, would be negative cosine x. And then the fourth derivative at x. So the derivative of negative cosine x. Well, cosine x, derivative of cosine x is negative sine x, and we're going to multiply that by a negative. So we're going to be back to sine x. And the whole thing's going to start all over again. Okay, so the fifth derivative of x. So you can definitely use the patterns in derivative of sine x and derivative of sine x and cosine x to do this without actually having to think too much. Okay, derivative of sine x is cosine x. The sixth derivative at x would be the derivative of cosine x is negative sine x. And then the seventh derivative at x is negative cosine of x. Okay, now f of 0. That would be sine of 0, and sine of 0 is 0. F prime of 0 would be cosine of 0, and that would be 1. And then f double prime of 0 is going to be negative sine of 0. Well, sine of 0 is already 0, so that's just going to be 0 again. And do you realize every time it's going to be sine, it's going to equal 0, okay? And then the third derivative at 0, that'd be negative cosine of 0. Cosine of 0 is 1, so that's going to wind up being negative 1. And then the fourth derivative at 0 would be 0, because sine of 0 is 0. And then the fifth derivative of 0 would be back to cosine of 0, which is 1. And then the sixth derivative at 0 would be negative sine of 0. Well, sine of 0 is 0, so this would be 0. And then the seventh derivative at 0 would be negative cosine of 0. Cosine of 0 is 1, so this becomes negative 1. Okay, and those are the first 7 derivatives for sine x, and their values at 0, right? Okay, so the way we write this is, because I'm going to slide up a little bit, is we're doing the partial sum, right? We're going to do the 7th order Taylor polynomial. Okay, so we're really doing a partial sum. Okay, and so we would write it like this: the 7th order Taylor polynomial of x would be f of 0 over 0 factorial. Now, if you just wrote f of 0, you'd be right, okay? And then plus f prime of 0 over 1 factorial times x to the first, plus f double prime of 0 over 2 factorial x squared plus f triple prime at 0 over 3 factorial x cubed plus the fourth derivative at 0 over 4 factorial x to the fourth plus the fifth derivative at 0 over 5 factorial x to the fifth power plus the sixth derivative at 0 over 6 factorial x to the sixth, and then finally plus the seventh derivative at 0 over 7 factorial x to the seventh power, right? Okay. Now, some nice things happen here because a lot of these, half of them, almost like half of them are zeros, right? So this one, f of 0 is 0. We're not going to have to worry about that one because that one's going to become 0. All right. F double prime of 0, that's also 0. So all the even derivatives are going to wind up being 0. So we're going to lose those out, right? And then this one's going to be, because it's the fourth derivative, is 0. So this numerator is going to be 0. So this one's 0. And then this one is going to be 0. And that would be pretty much it. Okay, so the seventh order Taylor polynomial, we're almost done, would be f prime of 0. F prime of 0 is 1. So that'd be 1 over 1 factorial. So that'd be 1 x to the first, or just x. All right, and then f triple prime of 0. F triple prime of 0 is -1. So it's going to be minus 1. Actually, I take that back. I'm gonna take these numbers right here, the numerators, and multiply it by x cubed. So it's gonna be 1 times x cubed, which would be x cubed. So minus, that's how it's normally written, minus x cubed over 3 factorial. And then f, the fifth derivative at 0 is 1, so that's gonna be plus, and it'd be x to the fifth over 5 factorial. And then the seventh one is a -1, so it's going to be minus, and this is going to be a 1 now because we changed it to minus, so it's going to be 1 times x to the 7th, so x to the 7th over 7 factorial. Okay, so that is the 7th order Taylor polynomial. So we're done with that part. We're done with the 7th order Taylor polynomial part. Now we want the Taylor series, okay, for sine of x, okay? So the Taylor series, we can actually use this to help us. That's why I didn't actually figure out these factorials, okay? You could, but you could also leave them just like this, all right, with the exclamation point for the factorial. All right, so let me write it like this. I'm going to say something in just a little bit that I want to add to this. Okay, so it's going to be x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the 7th over 7 factorial plus, I bet you can guess the next one, maybe x to the 9th over 9 factorial minus x to the 11th over 11 factorial plus, and I'm going to go dot, 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 plus, and then we want the nth one, right? We want the nth one. All right. So the nth one would look like this, okay? Now, it kind of switches now that we have this, right? We have this series. Now this is the, we could think of this as either being the first one or the 0th one, okay? And then this is the first one. If this is the 0th one, this is the first one, okay? And then this is the second one, and this is the third one, and this is the fourth one, and this is the fifth one, okay? So how do we get it to be positive right here, okay? It's because they're alternating, right? You should notice that, plus, minus, plus, minus, plus, okay? So we know there's going to be a -1 involved, right? A -1. And I'm going to raise it to the nth because I'm going to start this. This is going to be my 0th term. And this one's going to be my first term and my second term and my third term and my fourth term. It changes a little bit from this one, okay? All right. So you just have to make sure, really what you have to make sure is that what you write generates this series, okay? And then it'd be x to the, okay, so we need odd exponents, and then we need odd factorials down here in the denominator. So the way we're going to do that is, again, we're going to write x to the 2n, that'd be even, right? Plus 1, okay? And if we put 0 in here for that, remember the 0th term? That's the 0th term. If we put 0 in here for n, that's going to be 2 times 0. That's going to be x to the first, and that's what we have here is x to the first. So over, and then 2n plus 1 factorial. So that would give me 1 factorial underneath here, okay? So let's just make sure, okay, so if this is the 0th one, this is the first one, would this work? So we put 1 in for n. That'd be -1. Yeah, it'd give us a negative. X to the 2 times 1, that'd be 2 plus 1, 3. Yeah, it'd give me the third power that I need, right? So that'd be x cubed, and would also give me 3 factorial. This exponent and this factorial must match up, right? And they would, okay? All right, and then plus ... So it has to go forever to be the series, okay? And then this would be equivalent to sigma, and we would say n. Okay, now I'm using n in here, okay? It's interchangeable, okay? Some people use k, some people use n. So n equals 0, because I want it to start with the 0, 1, to infinity, and it would be -1 to the n. A lot of times this -1 is written out to the side of the fraction, times x to the 2n plus 1 over 2n plus 1 factorial, okay? Now, what is a Taylor polynomial series for? Well, it's for sine x. So if you go to infinity, this thing is equivalent to sine of x. Okay, now we've been talking about this interval of convergence, right? So it turns out that for this interval of convergence, it actually, if you go forever, sine x and this matches perfectly for all x's. So it's not just like, okay, the interval of convergence is from -1 to 1 or something like that, okay? It actually works. These match perfectly, but the condition is you have to go to infinity. So you have to have these ... plus the nth term plus ... And the ... dots here means it goes to infinity. In this sigma notation, we have the infinity right here that tells us we go to infinity. That's the only time that it's equal. So if you wanted to use this for sine x, you cannot, on the AP exam or even on my test, okay, you cannot use equals for the nth or the 7th order Taylor polynomial. Sine x and this are not equal. You could put approximately, but you couldn't put equal, okay? So sine x and this are equivalent for what's the interval of convergence. And there's absolutely no way that you guys understand like how I found the interval of convergence. It's just something I'm telling you right now, okay? There's no way. That comes up later in when we do convergence tests and all that. You know, the alternating series test and all that kind of stuff. Okay, so interval of convergence for this one is -infinity to +infinity. Okay, and that's that one. Okay, so I want you to, I think I may have stapled these out of order. Okay, so what I'd like you to go is to the table. Okay, and I'll pull that up next and show you guys. Okay, so you may have to go, I think it might be 2 pages away from where we're going to go next. Okay, all right. Okay, guys, so we're at this chart of the Maclaurin series, and a few things I want to talk about. Okay, one, there's a typo in this, and we need to change this x to the 0 right here. It should not be 0. Let's change that to n. It should be x to the n power. In fact, I'm going to cross that out. Let's just write x to the n power. Okay, so sigma n equals 0 to infinity, x to the n. Okay, another thing, when you're transferring some of these math type fonts from PC to Mac, some of the things change on us. Make sure that yours says ... Okay, a lot of times this comes out to be a capital L when you make the when we translate it from Mac to PC or PC to Mac. So just make sure this says ... on your sheet. I was printing these so fast, I didn't have a chance to check everything that I was printing out. And I'm afraid that this might be a capital L right now, okay? So just watch out for that, okay? Just if you see capital L's in all of these, it means ... okay? All right, so this first one is a power series that we studied, okay? And it comes from the geometric series, recognizing, oh, this is just like a geometric series. And this one right here is your first term, and then this x would be your r, because remember, it's a sub 1 over 1 minus r is the format for the sum of a geometric series. So this is a power series, and it comes from the geometric series. With r equal to x, okay? And this function 1 over 1 minus x and this series are exactly the same, all right? They're exactly the same if you go to infinity. So that's why you need the ... But it only works for x's between -1 and 1, okay? This one is also a power series, and it comes from a geometric series, right? And let's write this power series. It's a geometric series with r equal to, okay, so it has to be minus here, right? You have to be subtracting, so it's minus a negative x. So that's what our r is. R is negative x, okay? Now, this is also a Maclaurin series, Taylor series, okay? And it came from integrating, okay, 1 over 1 plus x. So this dx, this one came from integrating this one, and we went term by term and we integrated that, okay, and we came up with this series, right? Because remember, you can integrate term by term, a power series, and you wind up with a brand new series, okay? All right, now this one works between -1 and 1, but this one actually also works at 1, okay? All right, let me try focusing this. I don't know if I'm focusing very good. There, hopefully that's a little bit better, okay? All right, so this one, this Taylor series or Maclaurin series came from integrating 1 over 1 plus x. Tan inverse of x, okay, this one came from integrating 1 over 1 plus x squared dx. All right, and we come up when we integrate this, and we have the series for 1 over 1 plus x squared, and we integrate that series, we come up with this series, and it converges for -1 to 1, including -1 and 1. So everything in between and including -1 and 1. Now we're going to talk about why this one was 1 and this one includes -1 and 1 at a later lesson, okay? When we do, it's called convergence at the endpoints, okay? All right, so the next three, okay, you need to know these because it's going to make your life a lot easier, okay? We're not going to have to go through all the work that we just did, okay? If you have these memorized, where we had to find the first derivative and the second derivative and the third derivative, we can modify these, and you're going to see in the next few examples, you can modify these and get a brand new series just by, putting in a power here or taking sign of something, or even multiplying these. And I'm going to show you that in a minute, okay? So these, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Now really, right here, this is x to the 0 over 0 factorial, and this one's x to the first over 1 factorial. Well, why aren't we writing the factorials? Because 0 factorial and 1 factorial are both 1. So that's why you're not seeing them here. But underneath this x is really a 1 factorial, and underneath that, well, actually this 1 is x to the 0 over 0 factorial, which makes 1, okay? Now, this e to the x, these three are really important because actually these work for all x's. So the convergence is -infinity to +infinity for all three of these, okay? So I marked these three because you really need to have these memorized. It makes it so much easier if you just have them memorized and you know it, okay? If you notice earlier, sine x, it came up with only the odd powers, right? So let me explain why that happens, okay? So the odd powers, we're only getting odd powers, and it's because sine x is an odd function. And if you remember from last year, what that means, if it's an odd function, it means it has rotational symmetry, okay? You can rotate it 180 degrees and you have the same graph, okay? And then cosine x, why is that one all even powers? It's even powers, and this is why. It's because sine x is an even function. Not sine x, cosine x, I think. So cosine x is an even function. Okay, and this works for negative infinity to positive infinity, and this one's negative infinity to positive infinity. Okay, and that's that. I'm going to show you like how this matches up. Okay, if we do x and then we do x cubed, man, we add this one and we'll go 3 terms and 4. And if you can see, it starts matching up as we go on and on and on. I'm going to show you that with Geometry Sketchpad. Okay, and my little demonstrations that I usually use for you guys in class. Okay. Okay, guys. So here we go. So this is the sine function that you're seeing right here. Okay, and I want to show you what the Taylor series looks like. Okay, so if we do the first, it would be x to the, it would just be x, and that's what that looks like. Okay, so the sine function and the line y equals x kind of match up, right around x equals 0. Okay, so now we're going to add one more term to this. So x minus x cubed over 3 factorial. Okay, and that would be this third one. Okay, and so it's, excuse me, it's a cubic. All right, and that's why it's this curve. And see how it starts to match a little bit more. And then if we go x to the 5th, we're going to get it to match even more. And you see how we're wrapping the function with these polynomials. And then we can go x, or the 7th order Taylor polynomial, and that would be this one. You see how it's going further and further out. And then we can go to the 9th one, and the 9th one, it goes even further out. And if we keep doing this and go further and further out and we go to infinity, it's going to completely wrap the sine function, which is just kind of crazy stuff, I think. All right. Okay, for this next example, we're being asked to construct the 6th order Taylor polynomial and the Taylor series for cosine x at x equals 0. Okay, so if you wanna construct this, okay, the 6th order, that means you need up to x to the 6th power. So you need an x to the 6th power, and that'll be the last one. Okay, so here's where this chart comes up handy. Okay, so we're gonna write p of 6, because this is the representation for a Taylor polynomial and a 6th order, okay, of x. Okay, so having that chart memorized, first e to the x, sine x, and cosine comes in handy here. So this is going to be 1, okay, minus x squared over 2 factorial. Okay, that would be a 2nd order Taylor polynomial if we stopped right here. So then we need to keep going. So plus x to the 4th over 4 factorial. That would be a 4th order Taylor polynomial. And then minus x to the 6th over 6 factorial. And then that would be the 6th order Taylor polynomial. Okay, so that's the 6th order Taylor polynomial. Okay, now we need to do the Taylor series for cosine of x. Okay, so this would be cosine of x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus x to the 10th over 10 factorial plus dot 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 plus, and then this would be negative 1 to the n x to the 2n over 2n in parentheses factorial. So the 2n needs to be in parentheses because otherwise it's just n factorial, 2 times n factorial, and it's not 2n factorial. Okay, so remember that. Okay, and then we need to add plus dot, 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 because it has to go forever. Okay, this one's really, really important because this was the one part that means it's going over. This just means we're skipping a bunch of terms, okay? And again, you would not have to go up to the 10th power. I know I did. You wouldn't have to do that, okay? Maybe the first 4 or so, okay? And then this in sigma notation would be sigma n equals 0 to infinity of -1 to the n x to the 2n over 2n factorial. And that'd be the Taylor series for cosine x at x equals 0. Okay, for this next example, we want to construct the 5th order Taylor polynomial and the Taylor series for f of x equals e to the 3x at x equals 0. Okay, and so we're going to use the chart to help us do this. Okay, so we know e to the x is equal to 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial. And I'm in plus dot, dot, dot. But what I'm going to do is I want a 5th order. So that's why I went all the way out to here, okay? So to do this, okay, we can construct a 6th order Taylor polynomial, okay? And we could say, okay, e to the 3x, all right, is equivalent to, and what we're going to do is everywhere we see x, we're going to substitute 3x because it's equivalent to this, okay? So 1 plus 3x plus 3x squared over 2 factorial plus 3x cubed over 3 factorial plus 3x to the 4th over 4 factorial plus 3x to the 5th over 5 factorial. Okay, so I'm going to construct this Taylor polynomial. Okay, so P, and we want 5th order, so I'm going to do 5, 5th order Taylor polynomial of x is equal to, so this becomes, I'm going to clean this up a little bit. This would be 1 plus 3x plus 9 over 2, because 2 factorial is 2 and 3, I'm doing 3 squared and 2 factorial, okay, x squared. And then 3 cubed is 27 over 3 factorial. So plus 3 cubed is 27 over 3 times 2, which is 6, x to the 3rd power. Okay, and then 3 to the 4th. So 3 to the 4th is 81 over, and then 4 factorial would be 4 times 3 times 2 times 1, which would be 24. X to the 4th, and then plus, and then 3 to the 5th is 243 over 5 factorial and 5 factorial. I'm going to grab my calculator. And 5 factorial, I believe, is 720. So I'm going to grab my calculator. And then 5. 120. Whoops, what was I thinking? 120. And then x to the 5th. Okay. Some of these can be reduced. So the 5th order Taylor polynomial would be 1 plus 3x plus 9 halves x squared plus, both these are multiples of 3. So 3 goes in 27 9 times. So 9 halves x cubed, and then 81 over 24. Is 27 eighths. So plus 27 eighths x to the 4th, and 243 divided by 120, and That's 81/40ths plus 81/40ths x to the 5th. Okay, and that's the 5th degree Taylor polynomial for e to the 3x. Okay, now the Taylor series, okay? So now for the Taylor series, e to the 3x is equivalent to 1 plus, and then 3x plus, and then 3x squared over 2 factorial plus 3x cubed over 3 factorial plus 3x to the 4th over 4 factorial plus dot 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 plus, and then this would be 3x to the nth power over n factorial plus dot dot dot. Okay, so this could be cleaned up a little bit, right? So this could be 3 to the n, x to the n over n factorial. So that's how we're going to write this. Okay, so in sigma notation, okay, this would be equal to sigma n equals 0 to infinity of 3 to the n, x to the n, all over n factorial. And that's the Taylor series, okay, for e to the 3x, okay? All right. Okay, for this last example, example 6, we want to be able to write the first 4 non-zero terms and the general term. Now, general term means the nth term. Okay, for the Maclaurin series, which is a Taylor series for fx equals cosine of 2x. So when they say Maclaurin series, it's centered at x equals 0. Now the next lesson on Taylor series is we're going to do it where it's not centered at x equals 0. Okay, so that's coming up. Okay, but all of what we're doing today is really Maclaurin series because we're centering it at x equals 0. Okay, that's where the convergence is centered at. Okay. All right, so the first 4 non-zero terms. Okay, so f of x equals cosine of 2x. Well, what we want to know is, okay, we want to do cosine of x, okay? So cosine of x, I would write this, okay? So cosine of x is equal to 1 minus x squared over 2 factorial. That's the first 2 non-zero terms, okay? And then plus x to the 4th over 4 factorial. That's the first 3 non-zero terms. And then minus x to the 6th over 6 factorial, and then plus dot dot dot. Okay, so plus, and then the nth term, okay, would be -1 to the n power. All right, and then x to the 2n power, 2n over 2n factorial, right? And remember, this is the 0th term, which would make this +1, which would make this power be 1. Okay, no, sorry, power be 0. And this would be 0 factorial, and that would give you this first one, right? Okay, so that's the nth term. Okay, so plus dot dot dot, that's the nth term. Okay, to do cosine of 2x, and we want to do the first 4 non-zero terms, okay, cosine of 2x, well, all we're going to have to do is everywhere for cosine x, everywhere we see x, replace it with 2x, okay? So this becomes 1 minus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial minus 2x to the 6th over 6 factorial plus dot 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 plus -1 to the n 2x raised to the 2n power over 2n factorial. Okay, so we're going to clean this up a little bit. Okay, so cosine of 2x would be 1 minus, and this is going to be 2 squared, okay, which would be 4 over 2 factorial, which is 2. So this is minus 4x squared over 2, and then plus 2 to the 4th. Well, 2 to the 4th is 16. So this is 16x to the 4th over 4 factorial, which is 24. And then minus, and then 2 to the 6th, which is 64 x to the 6th over 6 factorial, which in 6 factorial is 720, okay? And then plus dot, 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 plus -1 to the n, and this becomes 2 to the 2n, x to the 2n, all over, and you can do it all over, or you can put the -1 out in front, 2n factorial, okay? Some of these reduce, so cosine of 2x, the first 4 non-zero terms are 1 minus 2x squared. And then 16 over 24, that reduces to 2/3. So plus 2/3 x to the 4th. And then the minus the 64 over 120, that reduces to 4 over 45. So minus 4 over 45 x to the 6th plus dot, 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 plus, and then again, this -1 can be out in front of the fraction or it can be on top like we have it. You could do it either way. I'm going to write it the other way. So -1 to the n, and then 2 to the 2n, x to the 2n over 2n factorial, okay? And then plus dot, 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 and we should have done that up here too, and here too, okay? All right, so that's the 4 non-zero terms and the general term for the Maclaurin series of fx equals cosine of 2x. So we can write these functions as series, okay? All right, so one more thing that I want to show you. Okay, so this is another, I don't want to say it's an example, but just another way of looking at these and how to modify it, okay? So what would be like something like this, the square root of x times cosine x? How would you come up with a Maclaurin series for this, okay? Well, we can do the square root of x times the series cosine x, okay? So we're going to do it like this. The square root of x is, or the square root of x times, and instead of cosine x, we're going to put in the series. So 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, dot, dot. And we could do this, okay? All right, so the square root of x is really x to the 1/2, right? So this becomes x to the 1/2 times 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, dot, dot. Okay, so really to come up with a brand new series for this Taylor series, Maclaurin series, okay, we just need to distribute this x to the 1/2, and we would have a brand new series for the square root of x times cosine x. So this series would look like this. It'd be x to the 1/2 and then minus, okay, and because we're multiplying bases that are the same, we're going to add the exponents. So this is 4 halves plus 1/2, which becomes x to the 5 halves. So minus x to the 5 halves power over 2 factorial, and then plus, okay, this is 8 halves, right? Because 8 halves is 4, plus the 1/2 is 9 halves. So plus x to the 9 halves over 4 factorial, and then minus, and then this is 6 is 12 halves. So this would be minus x to the 13 halves over 6 factorial plus dot, dot, dot. And then you could write you could continue on and write the nth term or the general term and write in sigma notation and all of that, okay? But this would be the Taylor series, okay, or Maclaurin series for the square root of x cosine x. So you can take these series and multiply by things to get a brand new series, okay? So that's the whole point of this, is we can take these 3 basic ones and modify them to come up with a brand new one, okay? All right. Okay, so I'm back with you now, and what I want you to be able to do, okay, for the assignment sheet is I want you to do assignment 11-2, and it's page 496, 1 through 12. And I'm going to put, these dates aren't going to match up at all, okay? It's just when I did the recording, okay? So this was on March 22nd, second, okay? You guys, I know these are very long videos. They were very long to create, and you have no idea how many takes it took um, to get these right. So this is intense, okay? And I hope you're getting something out of these videos. I hope they're helping you. And please, please, please feel free to reach out to me, email, remind, make a comment on Google Classroom, all of that stuff, because we're all in this together. We're working together through all this kind of craziness right now, okay? So just hang in there and just be tough, okay? All right, you guys take care. Bye.